Okay, hi everyone. So in this video, we're going to be looking at some problems on metric spaces. So in this first problem, we want to prove Cauchy-Schwarz inequality for function space. Um, so we know that there's a general result for this, which is Holger's inequality. But this is the case when uh, P and Q are equal to 2. So where this is used, if we want to, for example, prove that the space of all continuous functions um, is a metric space. So to show that the space of all continuous functions on a closed interval, closed and bounded interval AB, so with the mapping given by, so let's say D of FG, I'm going to define this to be so I'm going to subtract these two functions. So it will be F of T minus G of T. And I'm going to take the modulus of it, and then I'm going to integrate. Then I'm going to square it and integrate it over AB. Okay, and I essentially want to show that this space here, dt, is a metric space. Yeah, so this has to be a square root of all of this. Okay, so we want to show that the space of continuous functions on closed interval AB with this mapping defined for all f and g in this space is a metric space. So in other words, this Cauchy-Schwarz inequality for function spaces is used when we want to show that this metric above here, which is sometimes written as the D2 metric on function spaces, is a metric. So that is D is a metric. Okay. Okay, so let's see the proof of this. So in the proof of this, to make writing everything simpler, I'm going to make a following definition. Okay, so I'm going to define, so this object, and I'm going to define, will turn out to satisfy all the properties of a norm. Now we haven't proven that it's a norm, but if I refer to it as a norm, it's only because it does satisfy all the properties of a norm, but that is something that you may have to prove later on. But I'm going to define this object, and I'm going to call it the norm of f to simply be one of these. Okay, so I'm going to define this thing here to be the norm of f. So this is something I call the L2 norm. It's just going to be the integral from a to b of the modulus of f of t squared dt, and then I'm going to take the square root of it. And the reason why I'm going to define this is because it's going to save a lot of time when I have to rewrite this object over and over. Okay, like I said, that I'll put over here, you can show that this is a norm. And so you can actually show that this thing here is the norm. That's a hint about why they use this symbol with the two vertical lines, because it turns out to be a norm. Okay, so I could therefore rewrite, um, so we can rewrite the Cauchy-Schwarz inequality as, so using this new notation, I could rewrite what I want to prove in terms of this symbol. Because this is just the norm of fg, and I need to square it because there's no square root on the left hand side. And I want to show that this thing here is less than or equal to the norm of f by the norm of g. Okay, no, it's not the norm here. It's the inner product, but I don't want to write the inner product. Okay, let's just write the left hand side. Let's keep the left hand side the same. Because I don't want to write inner brackets because then I have to define what that is. Okay, so we'll just leave it like this. So so therefore we could rewrite the Cauchy-Schwarz inequality as this, and if you want, you could call this guy 1. So this is what I want to prove here. Now notice, so we could say if, let's say, for example, the norm of f is equal to 0, or the norm of g is equal to 0, then from the definition, how I define this, that will imply that f is identically 0, or is g is identically 0. And again, this is only because f and g are continuous functions. Remember, if f and g were not continuous functions, for example, um, if f was a function like this, where it was 0, and then it was non-zero for 1 point, and then it continued to be 0. Okay, so if this was your function f, then the integral of this function from a to b will be 0. But f is not the 0 function in this case. So what I'm saying is, the only reason that we could write this line here is because the functions are continuous functions. We are in the space of continuous functions. Okay. So if the norm of f or the norm of g is equal to 0, then either f or g is equal to 0, which implies that inequality 1 holds. Or you can say holds trivially. Okay, let me just say holds. Because in that case, both the left-hand side and the right-hand side will be 0. So, so if either one of these guys is 0, the inequality holds. So I'm going to assume that they are both non-zero. I'm going to assume that the norm of f is not 0, and that the norm of g is also not equal to 0. Okay. Now I'm going to define, again, I'm going to let's just say alpha be equal to the modulus of f of t divided by the norm of f, and I'm going to let beta be the modulus of g of t divided by the norm of g, because I know that the norm of f and the norm of g are non-zero, so I can divide by them. Okay, so alpha and beta are obviously strictly bigger than 0, right? These guys are obviously strictly bigger than 0 because they can't be negative, because you have the modulus, both numerator and denominator are positive. So both alpha and beta are strictly positive. And I'm also going to recall This is the result that says the if I have um, I have that for any, okay, let's do alpha and beta then. For any uh, alpha and beta, uh, actually we could say for any alpha and beta um, real numbers, then the modulus of alpha beta is less than or equal to alpha squared plus beta squared over 2. Yeah. So if you can't quite remember, if you can't quite remember if this is correct, we could always check this by doing a little proof, because the proof of this is not very difficult. In order to prove this, we just need to expand. I'll put here as a side. If I want to prove this inequality, I just need to expand alpha plus beta all squared. Right? And that of course is equal to alpha squared plus beta squared plus 2 alpha beta. Okay, and from this, this implies that so this guy is equal to this guy, therefore alpha plus beta all squared is bigger than or equal to 2 alpha beta, which implies that alpha beta is less than or equal to oh sorry, doing the wrong thing. So to be this is positive, right? So that means this guy here is always bigger than or equal to 0. Yeah, so this is why. So then we could get minus 2 alpha beta here is less than or equal to alpha squared plus beta squared. So alpha beta is greater than or equal. Oh, we need to prove modulus of alpha beta. So let me multiply by minus or divide by -2, and I'll flip the inequality sign around. So what I'm saying is this implies that alpha squared plus beta squared divided by minus this divided by 2 is less than or equal to alpha beta. And I also need to just expand. So now we just need to do the same thing, but instead of expanding alpha plus beta, we're going to expand alpha minus beta. And if you want, we could call this 2. And I know that 0 is always less than or equal. So now I'm just going to expand alpha minus beta all squared. So that is alpha squared plus beta squared minus 2 alpha beta. And again, we do the same thing. We make alpha beta the subject. Or we leave alpha beta on one side and dump everything else over to the other side. So I'll get, if I move alpha beta over to the left, I get 2 alpha beta is less than or equal to alpha squared plus beta squared. So alpha beta is less than or equal to alpha squared plus beta squared all over 2. Okay, and I could call this 3. So from inequality 2 and inequality 3, I could get from 2 and 3, I could get minus alpha squared plus beta squared all over 2 is less than or equal to alpha beta is less than or equal to alpha squared plus beta squared over 2. Okay, maybe I should have done this horizontally. Oh well. So from this, and this is the same thing as saying that modulus of alpha beta is less than or equal to alpha squared plus beta squared all over 2, right? So that is what we wanted to show. So if you can't remember it, then it's not too difficult to just check it. But if you remember it, you don't need to check this. Okay, so that's where this result comes from. And so where am I going to use this result? Well, I already defined up here an alpha and a beta. So I'm just going to plug in that into this result, which gives, okay, so alpha is modulus of f over norm f, and beta is modulus of g over norm g. So I'm just going to plug that into this result, that this inequality that we just proved. And this 2 in the denominator, I'm also going to take it across to the left-hand side. So that will give 2 into modulus, and it's alpha, so that is modulus of f of t all over norm f. Now remember, each of these terms are non-negative. Well, actually, each of these terms are positive. So this modulus on the outside, you don't really need it. So this is alpha, this is alpha, and beta, which is g of t, all over norm g, right? This is beta. And this guy is less than or equal to alpha squared plus beta squared. So it's less than or equal to modulus of f of t squared all over norm f squared plus modulus of g of t squared all over norm g squared. Yeah. So you get this result, and we're just going to simplify things down a bit, and that should give Cauchy-Schwarz inequality. So the modulus sign that we see in here, we can actually get rid of it because we have modulus on the outside. So we don't really need the modulus on the inside. And these two terms in the denominator, the norm f and norm g, I could pull those outside the modulus. Okay, so in other words, what I'm saying is I could reduce this to 2 over norm f, norm g. Remember, norm f and norm g are just numbers, by the way, because if you look at how we defined it, norm f is the definite integral of f of the modulus of f squared over the domain AB, and then you square root that. So when you work out what norm f and norm g is, that's just a number. So norm f and norm g are just fixed numbers. So we could pull those out from the modulus. We don't have to worry about anything with a sign, because this we show for this particular case is positive. It's a positive number. I want to get in here is modulus of f of t, g of t. Right? I don't need the modulus over each one because I'm taking the modulus over all of them in the end anyway. And yeah, so this is less than or equal to, we could write back the same thing here, all over norm f, and again, norm f squared is just a number, plus modulus of g of t squared, and norm g is just some number. Okay, and if we look at what we have to prove, there is an, so what I'm making here on the left-hand side is the left-hand part of the Cauchy-Schwarz inequality. That's actually what I'm making here on the left. So you see I have to integrate this from A to B. So I'm just going to integrate both sides from A to B. Okay, so I'm going to integrate both sides from A to B, and of course 2 over norm f, norm g is just some constant, so I can actually pull that outside of the integral. So 2 over norm f. Norm g is just some constant, so I could pull that out and then I can integrate from a to b of modulus of f by g dt is less than or equal. Then it's the integral of over the right-hand side, and the right-hand side is a sum, and you know that the integral of a sum is the integral of each term. Okay, so this is just the integral from a to b of this guy all over norm f squared dt plus integral from a to b modulus g squared all over norm g dt. Okay, and again, the roots that I'm using there is the if you have, for example, I don't want to use back F and G. Okay, let's use back. um, let's use capital F and capital G. If I have, like, for example, capital F of t is less than big G of t, then I'm using this fact that the integral of this one is less than or equal to the integral of this one. Okay, so that's what I'm using there. And now we're pretty much finished, because we just need to make one little observation on the right-hand side. Okay, so the left-hand side is the same. Okay, we could break this up into 2 steps, but if you could see it now, then that's fine. And the observation is that each one of these terms on the right-hand side is actually equal to 1. So how am I getting that? Remember that the norm of f squared, this term in the denominator, is just some fixed number. And we could pull numbers out from the integral. Okay, so I'm just going to pull that guy out from inside the integral. And this is just integral from a to b of this term. Right, and I'll do the same with the g's, because the norm of g, again, I think that should be squared. Very well. Yeah, that should be squared. And the norm of g is just some fixed value. So I could pull out the norm of g squared from the integral, right? Those are just fixed numbers. And you could pull constants out from the integral. And what you then need to just observe here is that this number here, this is precisely the norm of f squared. And this guy here is precisely the norm of g squared. So the norm of f squared will cancel with 1 over norm f squared, and the norm of g squared will cancel with 1 over norm g squared. So what we get is 2 over norm f, norm g, integral from a to b, f of t, g of t, dt is less than equal, and this guy here is 1, this guy here is 1, which is equal to 2. And I'm just going to now cancel 2's on both sides and take this guy over to the right-hand side. Okay, so the last line here will be the Cauchy-Schwarz inequality. So there's a few little tricks in proving it, but once you remember the tricks, the actual arithmetic is a bit straightforward. Okay, so this guy is less than or equal to norm f, norm g, and I believe we call this 1. Yeah, so this is our inequality 1, which is the Cauchy-Schwarz inequality. So this is 1. So that's the proof of the Cauchy-Schwarz inequality for when we're dealing with this particular metric on functions. Okay, so now that we have the Cauchy-Schwarz inequality, well, what could we do with it? We could use that to actually prove this next inequality, which is the Minkowski inequality for function spaces. And again, this is actually a special case of the Minkowski inequality for LP spaces. In that case, where you have 2 over here, it's replaced with P, where P is between 1 and infinity, right? And this will still work. To prove that more general inequality, you need something more general than the Cauchy-Schwarz inequality. You need Holder's inequality. But if you're just proving the case for when P equals 2, which is what we have in this case, then you don't need full Holder's inequality. You could prove this using simply the Cauchy-Schwarz inequality. Okay, so how to prove this again? So again, so just like with the Cauchy-Schwarz inequality, to keep from having to write this integral from a to b of f and modulus of f squared, then square root and all of that. Again, we're going to let this symbol here, and again, this will actually be a norm. So I'm just going to call it norm f. So again, I'm just going to define this to be same thing like with the Cauchy-Schwarz inequality, integral of a to b modulus of f squared dt, then I'm going to square root all of this. Okay, so this was the same definition that we just used to prove the Cauchy-Schwarz inequality. Again, we're going to define it the same way. And now, so in the proof of this, I could rewrite this Minkowski inequality in terms of this norm notation. So in other words, I need to prove, if you look at what I have here on the left-hand side of this inequality, and if you look at how I define this norm, this is simply the norm of f plus g, right? That is simply the norm of f plus g. And it must be less than or equal. And this first term over here, well, that's just the norm of f. And this second term, well, that's just the norm of g. Again, this should look familiar to you. This is the triangle inequality. In fact, this is the triangle inequality for the norm. So, so by proving this, we actually proven, we're actually doing part of the proof to show that this object that we've defined with these 2 vertical lines on each side really is a norm, because this result, Minkowski inequality, is the triangle inequality, which is one of the properties a norm needs to have. Okay, but we're not really interested with the norm, we're interested with the metric. Okay, so this is what I need to prove. So let me call this equation or inequality 4. Okay. So the only little trick you need to remember is how to start, and that is very easy. So instead of starting, so if I want to prove this inequality, I could either take the left-hand side and show it's less than or equal to the right-hand side, or I could take the right-hand side and show it's less than or equal to the left-hand side. It turns out it's easier to start with the left-hand side, but we're not just going to start with the norm of f plus g, because the reason for that is because if you look at how I define the norm here, it has a square root with it, right? So this term here has a square root with it. And I don't really want the square roots to come in just yet. So I'm going to work with the norm squared. Okay. So this is just equal to, by definition, the integral from a to b, it will just be this left-hand side without the square root. So it's the integral from a to b modulus of f of t plus g of t squared dt. Okay, and I don't have the square root here because I'm taking the norm to be squared. And I'm just going to use this, and in the last step, whatever I get, I'll just square root both sides and try to recover the Minkowski inequality, which is what I'm after. Okay, so I want to basically break up this term into two terms. Okay, and so again, we could see that if, for example, how do I want to say this? If I have something like a plus b squared, okay, so we know that is equal to a squared plus b squared plus 2ab. Okay, and so therefore this is the left hand side will be less than or equal to okay, sorry about that. We actually don't need that. It's actually simpler than that. Yeah, so to break this up, I'm just going to use triangle inequality for modulus. Right, so that is just, so this inner term, so forget about the squared, this inner term, the modulus of f of t plus g of t, yeah, so it's actually much simpler than that. Is just less than equal to the modulus of f of t plus modulus of g of t, right? And then you just square both sides. So this is less than or equal to the integral from a to b of the modulus of f of t plus the modulus of g of t, and I just square both sides. So I'm just put like a break bracket like that and square both sides. Right, so from this, I could square both sides. Yes, f of t plus g of t squared less than equal, right, to the squared plus, again, this works because both left and right hand side are non-negative. Okay, and what I do is, oh, sorry, it should be squared over both, or over everything, right? Over everything, yeah. And then I just integrate both sides and I get this line here. Okay, and now what I'm going to do is I'm just going to square out these terms, right? So this is integral from a to b. So a plus b all squared is equal to a squared plus b squared plus 2 times ab. So 2 into of t mod g of t dt, right? So this whole thing dt. And from here, I could break this up now into the integral of each of these terms. So this is the integral from a to b of modulus of f of t squared plus dt dt plus the integral from a to b of modulus of g of t squared dt plus, and this 2 I could pull out from the integral, 2 and 2, integral ab, and you of course know that the modulus of alpha by the modulus of beta is equal to the modulus of alpha beta. So I'm going to push f and g together under one modulus. Okay, so I get this term over here, and this last term here is the integral of a product. So this last term is what we're going to apply Cauchy-Schwarz inequality to. And notice that this first term here, this is just the norm of f squared. This second term is just the norm of g squared, right? And this guy here is the left-hand side of the Cauchy-Schwarz inequality. Okay, so this is less than or equal. I'm going to replace this first term by norm f squared. I'm going to replace the second term by norm g squared. And the reason why it's less than or equal is because I'm applying Cauchy-Schwarz inequality to give me that this guy here, the last term, is less than norm f norm g. Right? That's what we just proved. So by the Cauchy-Schwarz inequality. Okay. Now, this right-hand side is simply norm f plus norm g all squared. Okay. And so the left-hand side is norm f plus g all squared is less than or equal to norm f plus norm g all squared. So I'm just going to square root both sides. So just square root both sides. Or if you want to, we can write out a statement. We'd say maybe hence the norm of f plus g all squared is less than or equal to this guy. Norm f plus norm g square all of that. So square root both sides because again, these are non-negative numbers. So we get the norm of f plus g is less than or equal to the norm of f plus the norm of g, which is 4. Okay. That was equation number 4, or I should say inequality number 4, which is what we wanted to prove. Okay, so uh, which is inequality 4, and that is of course the Minkowski inequality. Okay. So that's the Minkowski inequality. So I said that in the beginning that all of this is really used when we want to show that the space of continuous functions or closed and bounded interval AB with this particular metric, well, is a metric space. So this is used when you want to verify that this map is indeed a metric. So we could go ahead and now that we have the Minkowski inequality, which will help us prove the triangle inequality, we can go ahead and write out a little statement for why that is the case. So I'll put the aside the Minkowski inequality above can then be used to show that this space, I'll put C, A, B, comma, D, where, remember we defined the distance between two functions. We are going to subtract their function values, take the modulus of it, square it, integrate it from A to B, and square root this whole thing. Is a metric space. Okay. And let's just write out the proof because now if we have the Minkowski inequality, uh, it shouldn't be too difficult to write out this proof. So for metric, remember the properties, it has to be positive definite. It has to be zero if and only if the 2 points that you put in is zero. It has to be symmetric, and it has to satisfy triangle inequality, which is what the Minkowski inequality will allow us to do. Okay, so we can write out the statement for each of these. So let F and G belong to, I'm going to call this X. I don't have to keep writing it. So let F and G belongs to X. Then, well, clearly, by the definition of what this distance, so we can't say it's a metric yet, but it will be a metric. But clearly, by how we define this map, it will be bigger than or equal to zero because I'm taking the integral of a non-negative function since it's always squared, and then I'm taking the square root of it. So this number, whatever I get here, is non-negative. Okay, so clearly the distance between f and g is always bigger than or equal to zero, and of course, it's easy to see that df of g, I could just switch these two functions around and nothing will change. So this is equal to dgf, right? So I have positive definite and symmetric. Um, Now for if I set f equal to g, right? Then this implies that dff, right? Well, that's just equal to the integral from a to b of zero, okay? Which is equal to zero. Okay? So when I put in the same point, I get zero. However, if this if the distance between 2 points, f and g equals zero, you have to be careful here because since you're dealing with the integral, that does not always mean that the two functions are the same. So what I'm saying is for d of f and g equal to zero, right? That only implies that f and g are equal to each other um, since f and g are continuous functions. If, for example, if the space was not the space of all continuous functions, if it was just the space of all integrable functions, then this will not work because you could have two integrable functions, f and g, such that when you work out this value, d of fg, it will be zero, but those two functions would be may not be the same. Okay, they could differ by a countable number of points. Okay, that's because the integral, remember the integral doesn't care about what's happening at a particular point, it just integrates over. So I'm talking about, for example, if you have like a removable discontinuity, the integral doesn't care about it, it just integrates over it. And that causes a problem, but of course you don't have those type of discontinuities if you are only dealing with continuous functions. So what I'm saying is that this um, the next part of this implication only holds because of the space we are in. Okay, and the fg equals zero if and only if f equals g, right? And this only holds because we are only looking at continuous functions. If we were not looking only at continuous functions, this may not hold. Okay, so now the last one is uh, triangle inequality, right? So the triangle inequality um, is given by Okay, so let's just write out what it is. So it'll be D of FG is less than or equal to D of, let's say, F with H plus D of H with G. Okay, where F, G, H belong to X. So this is what I want to prove. So now I can just invoke the Minkowski inequality because we've already done all the work to come up with that. Remember that, um, so we're still going to just use how I define this norm. So the norm of a function is the integral of the modulus squared of it, and then you take the square root of it. So if you look at what DFG is, if you look at the definition of DFG, right, that's simply DFG. If you look at the definition of it, that's just the norm of F minus G. Okay, that's just the norm of F minus G, how we define this particular norm. And the usual trick is that we add and subtract this function H. Okay, so F minus H plus H minus G. Yeah, and since we just proved Minkowski inequality told us what this, how to deal with this. That is, if you have the norm of the sum of two functions, that's less than equal to the sum of the norms. Okay. So I'm taking this guy as one function and this guy as one function. So this is just less than or equal to the norm of F minus H plus the norm of H minus G. That is, of course, by Minkowski inequality. Right? And the norm of F minus H is simply D of FH. And the norm of H minus G is simply D of FH. Right? And the norm of H minus G is simply D of HG. Okay, which is what we wanted to prove, the triangular inequality. So the triangular inequality follows very easy once we've done all the work to derive Minkowski inequality. So therefore, x, which is equal again to space of continuous function on AB with this metric, which is the D2 metric, is a metric space.